Okay, so in this video, we will look at slightly more subtle examples of U-substitution. So examples where we're not just looking for a function whose derivative is multiplying the expression, but slightly more subtle possible change of variables. So let's start with a simple example. What if I integrate the square root of x times 2x plus 3 dx? Well, this is quite easy, right? Let's replace the square root of x by a power of 1/2. So x to the 1/2 times 2x plus 3. If we multiply out, we will have individual powers of x, and then we can use, quite simply, the power rule. So x to the 1/2 times x, well, 1 plus 1/2 is 3/2, so it's 2 times x to the 3/2, plus 3 times x to the 1/2. And now we are integrating over a sum of powers of x, so we can use, quite simply, the power rule. 2 stays there, constant multiple. The power rule says, as always, we add 1 to the exponent. 3/2 plus 1 is 5/2, and we divide by the new exponent, 5/2. Plus, 3 is a constant multiple, so it stays there. Times, power rule once again, we add 1 to the exponent. 1/2 plus 1 is 3/2. And we divide by the new power, 3/2. Plus, of course, the constant of integration, c. And that's it. Of course, we'll clean this up. If you divide by a fraction, you multiply by the reciprocal. So over 5/2 is times 2 over 5, which will give you times 2, 4 over 5, times x to the 5/2, plus divide by 3/2, multiply by 2/3, but 2/3 times 3 is simply 2, times x to the 3/2 plus c, and that's it. So this was a rather simple integral, right? It was the square root of a single x. We could multiply out, power rule, and we're done. One last little thing. This is really an aside, but we could simplify a little bit by factoring common terms. There's a common factor of 2. Of course, if you take 2 out of 4, that leaves you with 2. And we can factor the smallest power of x being 3/2. So if you factor from 5/2, 3/2, well, 5/2 minus 3/2 is 2/2, which is simply 1. Factor 3/2 from 3/2, you're left with 0. X to the 0 is 1. That leaves you, of course, with 2 over 5x. So 2x over 5 plus the 2 we factored, plus 1 plus c. And if you want, you can write finally 2x to the 3/2 times, as a single fraction, 1 is 5 over 5, so we'll get 2x plus 5 over 5. Okay, so this last step was simply simplifying the expression, right? Factoring common factors, and then simplifying the leftover expression. But the point is, this was a rather straightforward problem. Multiply out by the square root, power rule, and you're basically done. What if, just for fun, we change the square root, and we don't put the square root on the first term, but on the second term? Let's see if this makes the integral more interesting. So we integrate now x times the square root being on the 2x plus 3 terms. Well, now the option that we had in the first case disappears, right? Before we had root of x times 2x plus 3, we could multiply out, use the power rule, and we were done. This option is gone now. This is root of a sum of 2 terms, we're stuck with this, times x, we're stuck with this. So the option of multiplying out the expression and using the power rule is gone. So it seems that we're stuck here. Well, why did it work in the first example? If you go back, it worked out Because we have the square root of a single variable. If the square root is on just one variable, 1x, then you can multiply out, and then you can use the power rule. And that's the key observation. If the square root was on a single variable, things would work out. Well, the square root now is not on a single variable, it's on 2x plus 3. But what if we give 2x plus 3 a new name? What if we let u be 2x plus 3? Now we are transforming the variable 2x plus 3, a sum of two terms, into a single variable. Hopefully, this should fix our problem. Let's see if it does. So, let's start replacing. Let's replace first the square root of 2x plus 3. Well, if u is the root of 2x, if u is 2x plus 3, then the square root of u is the square root of 2x plus 3. So that's just root of u. Well, what about x? Well, again, we want to replace x as a function of u. Well, this shouldn't be too difficult. We can isolate x here as a function of u. Subtract 3 on both sides. So u minus 3 equals 2x. Divide both sides by 2. And so u minus 3 over 2 is equal to x. So now you have expressed x as a function of u. It is u sorry about that. X is u minus 3 over 2. So we can replace x by u minus 3 over 2. And the one last thing to replace is dx in terms of du. Well, u is a function of x. Take the derivative on both sides. So du over dx. The derivative of u with respect to x, as u is a function of x. But the derivative of 2x plus 3 is simply 2. We need to isolate dx, so multiply by dx to the right. Therefore du is 2 times dx. But we need to isolate dx, not 2 dx, so multiply by 1/2 or divide by 2 on both sides. So 1/2 du is therefore dx. And now we can replace. dx is 1/2 du. So everything in terms of x is now in terms of u. And if you notice, the problem is gone. Because now the square root is on a single variable, so we'll be able to multiply out and use the power rule. So now we're right back to the problem of integrating the root of x times 2x plus 3. Let's clean this up. 1/2 times 1/2 is a quarter. Constant multiple, factor it out of the integral, which leaves you with replacing root by a 1/2 power, e to the 1/2 times u minus 3 du. And to integrate this, now we can multiply out by e to the 1/2. U is e to the 1. So we get 1 plus 1/2, 3/2. Minus 3 e to the 1/2. And now we can use the power rule, leaving a quarter up front. Add the 3/2 1, so you get u to the 5/2. Divide by 5/2. Minus 3 is a constant multiple, so it stays there. Power rule, add to 1/2 1, you get 3/2. Divide by 3/2. Plus, of course, the constant of integration. Let's clean this up a little bit. We have a quarter. Divide by 5/2, multiply by 2 over 5. U to the 5/2. Minus, divide by 3/2, multiply by 2/3, but 3 times 2/3 is 2, so minus 2. U to the 3/2. Plus, of course, c. And now, aside from replacing back in terms of x would be done, we'll do one simplification. Again, we'll factor common terms. We have a quarter. There's a common factor of 2. So we can factor it out. So times 2. So it's gone. Smallest power is 3/2. So factor u to the 3/2. So it's gone from here. 3/2. 5/2 minus 3/2 is 2/2, which is 1. That leaves us with u. And now we're good to go. We're left with u over 5 minus 1 plus c. And here, if you want, you can write this as u minus 5 over 5. Of course, 2 over 4 is 1/2, so it's u to the 3/2 over 2 times u minus 5 over 5 plus c. One last thing, 2 times 5 is 10, so we can simply say this is 1 over 10 u to the 3/2 times u minus 5 plus c. This is really simplified as best we can, and now, since we had the integral as a function of x originally, we have to give our final answer as a function of x. Let me remind us right here that u was 2x plus 3. So replacing 1 over 10, u, which is 2x plus 3, to the power of 3/2, times u, 2x plus 3, but it's u minus 5, plus c. Now we've replaced, we can simplify here a little bit, as 3 minus 5 is negative 2, so we have 2x minus 2, which gives us factoring 2 times x minus 1. So we can factor the 2 up front, and 2 over 10 is 1 over 5. So we get 1 over 5, 2x plus 3 to the 3/2, times the leftover of x minus 1, plus of course c. Here's our final answer, fully simplified. But, I mean, this was just the boring part, just straightforward, replacing u in terms of x and simplifying the answer in terms of x. What you have to remember is this was a special example of a U-substitution, right? We didn't let u be 2x plus 3 because the derivative was 2 and 2 was multiplying the expression. This was not the case. The idea was if the square root was on a single variable, then we could multiply out and solve this integral. So we've let 2x plus 3 become a single variable, and this fixed our problem. So here's a beautiful example of a subtle choice of a U substitution.